Today we are going to continue the amazing categorical methodology called discriminant analysis. So today we are going to cover linear discriminant analysis, quadratic discriminant analysis, and anything in between. Today's course needs a little bit of math background, and specifically what you need to know is Bayes' theorem. For those who cannot remember Bayes' theorem basically worked on switching or flipping the probabilities. For example, if you have probability of y given x, and you want to extract x given y from it, you use Bayes' theorem. For those of you who are not too sure what was Bayes' theorem, I highly suggest you review introductory probability before coming to the class, because some of the notation may look slightly strange if you are not familiar with Bayes' theorem. So in discriminant analysis, we use Bayes' theorem, and basically we assume that we have observations, and based on those observations, we are interested to find the probability of y being equal to some of the categories we have. And to estimate that, we are going to use probabilities of x given y. So we first find the probabilities of observing such an observation based on the category, fixed category, then multiply the prior probabilities and divide it by summation of prior probabilities and these conditions to get this part. So in the next slide, I'm going to get slightly deeper in it. We usually use normal distribution as a distribution on our categories, but this methodology can easily be extended to more generalized formats. For instance, we can use gamma distribution or any other distribution as long as we're comfortable with. But one of the cool things about using normal distribution is that if you use normal distribution and fix the standard deviation, you end up with some linear function. Always linear functions are of our interest. And if you use standard deviations as well in the Gaussian distribution, you do not fix that part, you end up with quadratic functions. Again, quadratic functions are easy to deal with. So in LDA and QDA, which is linear discriminant analysis, and quadratic discriminant analysis, what we're going to use is Gaussian or normal distribution. So let's focus on the Bayes' theorem first. And I think it's better that we work on some of the one or two examples on Bayes' theorem to remind you what it was. So for those of you who are acquainted with Bayes' theorem, you can skip, I don't know, the next couple of minutes of this lecture, but I think for those who are not, it's better to have an introduction. So we are interested to find the probability that our category is equal to k, given that we know some observations. For example, the probability of default, let's fix k to default. Probability of default, given that your balance is such, number of credit cards is such, and so on and so forth. So if you want to find this probability, what you can do is to find the probability that x is equal to x given y equal to k. That means, what is the probability of having this balance and this number of credit cards? Conditional on that, you are a defaulter times probability of default, and then you divide it by probability of condition. And as all of us know, we can break down this probability of condition to subparts. One case that we can observe x, which is this level of income and this level of balance, is based on the probability of being on k. Then we can sum it up to other categories. For example, what is the probability of getting x? So for this case, what is the probability of giving x given y is default times probability of default plus probability of x given y is no default given times probability of no default. Oh, I'm sorry for that. What happened? Okay, so we can break down probability of, and maybe it's better that I do it here with another. So probability of x can be written as, so probability of x equal to x, capital X equal to lowercase x is probability of x given default times probability of default plus probability of observing such an x given no default times probability of no default. If you have more categories that are happening, you can just break down probability of x onto this, and that's the basic. As you can see, on denominator, the order of x and y was switched. So I just wrote probability of x as this combination. So that is how you just change things, and that's how you can work on that. So let's work on some of the examples of Bayes' theorem. Let's say, let me fix that. Okay, here, okay. So let's say we are living in a class that 60% are female. So probability of being female in the class is 60%. Probability of being male is 40%. And let's say probability of, so for those who are female, so given that you're female, the probability that you're using an iOS device, which is, for example, iPhone, is 70%. Probability that you're not going to use iOS device is 30%, therefore. And let's say probability of you use an iOS device given that you're male is, let's say males tend to use less iOS device. So let's say it's 50%. I'm just making these numbers up to just make my point. This is equal to, let's say, 50% as well. So no iOS is also 50%. So let's say you randomly pick a person. So we randomly pick one student. What is the probability that that student is female given that you know that person is using iOS? So before, we knew what was the probability of using an iPhone given that that person was female. So if you knew that was if the student was female, there was 70% chance that she was using iOS device, and that's 50% for males. But here, the question is, what is the probability of using an iOS device given that you given that you're using an iOS device? What is the probability that you are female? So these two things are clearly different. So that is equal to probability of iOS given female times probability of being female divided by probability of iOS given female times probability of female plus probability of iOS given male times probability of being male. So that is indeed iOS given F was 70%, so 0.7. Probability of being female was 0.6 divided by 0.7 times 0.6 plus iOS given male is 0.5 times 0.4. So if we do the math, that will be 21 divided by 20, sorry, that is 42 divided by 42 plus 20, which is 62. So it's 21 divided by 31. I think 21 divided by 31 should be, so let's see, what is this probability? 21 divided by 31 is 67%. So that is 67%. So if our math is correct, then that is 67%. Okay, so what is probability of being male given you're using an iOS device? That is 33%. That is 33%. Okay. So as you can see, our prior belief about if you would randomly pick a person, there was 60% chance that that person was female. Now, since you know that person is using iOS, your revised probability is 67%. You are more sure that that person is female because usually females tend to use more iOS devices in our sample. Okay, so let's get back to the definitions we have. We can show that mathematically that for any density function that we have, we can write down the probability of being in a class conditional on your observations is equal to the prior probability of that class. So let's say probability of you being an iOS device is prior probability of you using iOS device times the marginal probability of you being in that class, which comes from the density function you have, divided by all other possible categories. So it's the same product for all other possible categories. So let's say you have 10 categories here. You can have an iOS device, you can have Android device, Windows-based devices, BlackBerry devices, and so on and so forth. So no matter how many classes you have, that will be the summation of all the things you have. So probability of x given y is the density function of x in class K, and this probability is called the marginal probability. So that's marginal probability times the density function of that probability divided by the marginal probability times the density, and this is called prior probability. So the posterior probability is a function of prior probability times density functions in each case. So let's look at some examples. Let's say we have two groups. So this is our green group, this is our pink group. The green group is normally distributed around -1.5. The pink one is also normally distributed around 1.5. Let's say in the beginning, 50% of our population were pink, 50% was green. It is not hard to show that for this category, if x is less than 0%, it's more likely that it will be green. If it's more than 0%, it's more than 0, it's more likely that it will be pink. In this right-hand side case, 30% of our group is green and 70% are pink. So as you can see, so let's say it's -0.5, this boundary is -0.5. We should have a more solid evidence to decide that belongs to category green. Before, anyone below 0 will be categorized as green. Now we need to have more solid evidence to conclude that that person belongs to green. So here you should be at -0.5 and below, and if you're more than -0.5, you categorize it as pink. Why? Because you have more pink people in your category. So one thing we can visually see here is that the more propensity, the more the prior proportion of one category, the more evidence you want to have against it in order to categorize in other categories. So let's ask ourselves, why do we use linear discriminant analysis to begin with, or any discriminant analysis functions? The quick answer is, unfortunately, logistic regression does a very, very bad job, if your data is well separated. For example, if your data looks like this, so let's say we have x1 and x2, and these are one category, these are another category. So as you can see, these categories are well separated. Logistic regression does awfully here. So the other thing is, if your number of observations is small and the distribution of predictors are approximately normal, then you can show it by simulation that discriminant analysis does better job than logistic regression. And the next one is if you have more than 2 categories, the interpretability of logistic regressions are almost gone. It's very hard to interpret them. And you can see that the linear discriminant analysis does a better job in that case. So if you have more than a couple of categories, more than 2 categories, it's better. It's not better, but it's easy to use linear discriminant analysis. If n is small and your predictors are normally distributed, then again, it does a pretty good job. And if your data is well separated, again, logistic regression cannot be used. So for all these reasons, we use discriminant analysis. So let's get back to our discriminant factors. So in linear discriminant analysis, we use Gaussian density function. And as you can remember, I think you can remember that the density function of normal distributions look like this. It's 1 over square root of 2 pi, is 3.4, times the standard deviation of that class, times exponential of negative 1 over 2. X here is your observation. So for every observation, that is the density you get. Minus its mean, so mu k is mean, divided by a standard deviation squared. So this sigma 2k is the variance of class K, so sigma k is the standard deviation of class K. In linear discriminant analysis, we assume all classes have same variance. So that is relatively strong assumption, but as we can see, it will make our life easier. So if you just write the base function, we can show that the probability of being in a class given X would be the prior probability of that class times its marginal probability divided by summation of all marginal probabilities times the density functions of each class. But since these guys are equivalent, you can easily cancel these terms. So you will be left with some exponential functions. So let me use some examples here to start our talk. Let's assume that male height is normally distributed with mean 6 feet and standard deviation 0.5. And let's assume that females height is normally distributed with mean 5.5 and the standard deviation 0.5. So this is my mean, this part was standard deviation. This was my mean, this was standard deviation. So one thing to remember is that in linear discriminant analysis, you assume sigma is the same in both categories. In both categories. So let's say in your population, 70% of your population was male, 30% was female. So basically, prior probability of being male was 70%, prior probability of being female was 30%. And now let's say you know that somebody's height is, let's say, 5 feet. So we want to see what is the probability that this person belongs to be female, or what is the probability that this person is male given being female, 5 feet. So let's focus on female. Male will be basically 1 minus the probability you find here. So this is equal to probability of being female times the marginal distribution as the density function of normal distribution at x equal to 5 feet, mu equal to 5.5 feet, and sigma b equal to 0.5 divided by probability of being female times same thing, f of f for x equal to 5 feet mu equal to 5.5 feet, and sigma being equal to 0.5, plus probability of being male times, I just write the rest here, probability of being male times f of being male for x equal to 5 feet, mu equal to 6 feet, and sigma being equal to 0.5. So that being said, probability of f for x equal to 5 feet will be prior probability of being female. So prior probability of being female was 0.3. As you can see here, it was 0.3. So that is 0.3 times 1 over the square root of 2p sigma, and sigma was 0.5 for females, times exponential of 1 over 2 x, which is 5 minus 5.5 divided by 0.5 squared, divided by. Same thing. So I just put this. That means same thing you had here. Or maybe it's better that I just write it. So 0.3 plus 1 over the square root of 2p, 0.5, exponential 1 over negative 2, 5, negative 5 minus 0.5 divided by 0.5 squared, plus probability of being, oh, this is multiplied, probability of being male, which is 0.7, times 1 over the square root of 2p, 0.5, exponential negative 1 over 2. Our observation is still 5, but the mean of males was 6 divided by 0.5. It's easy to show these terms will be cancelled. So that would be equal to 0.3 exponential. So this is 0.5 divided by 0.5 is 1, so exponential 1 over 2 divided by 0.3 exponential negative 1 over 2 plus. So that is 0.7 times. So 5 minus 6 minus negative 1, negative 1 over 0.5 is 2. 2 to the power of 2 is 4. 4 divided by 2 is 2, so it's exponential negative 2. And let's calculate that part now. So that is equal to 0.3 times exponential negative 1 over 2. Okay. 0.7 times exponential function of negative 2. Oh, okay. So that is 0.3. Okay. So that is this guy plus this one. So it's 65.76%. 65.67%. 65.67%. So the question is, given that you know that that person is 5 feet, is it more likely that she will be a female or he is a male? The answer is that there's more likely that she's female because it's 65% that she's female. And as you can see, the math was not too hard to do. We just needed to write down the exponential functions that we had, and we would be okay. So basically, it's nothing too fancy about it. You just find the probabilities. Before there was 70%. If you randomly pick a person, there's 70% chance that's a male, 30% that's female. That's prior probability, so it's more likely to choose a male. But given that you know her height to be 5 feet, it's 67% chance that we're dealing with a female instead of male. Now the second question I have is, So what is the boundary of our decision? So for 5 feet, we were extremely sure that that person is female. Now, how can we find a boundary by which to decide whether we are dealing with a female or male? So what is the X that gives you 50% chance? So let's look at this formula here. So let's say instead of X equal to 5, we had X. In order to this, for this equation to give you a 50%, this one should be exactly identical for males. So if pi f times ff is equal to pi m times fm, then there is 50% chance that it is female or male. So let's find the X. For that X, there is same probability that that you are dealing with a female or male. So in order to do that, we have to solve this equation. What I want to show here is that it's not easy to solve the equation this way. And that's why when we talk about discriminant analysis, you will admire the math behind it, because it makes our life so much easier. So pi f was 0.3. So 0.3 times 1 over the square root of 2 pi 0.5 exponential of negative 1 over 2 x minus 5.5 divided by 0.5 squared shall be equal to 0.7 times 1 over the square root of 2 pi 5 exponential of negative 1 over 2 x minus 6 divided by 0.5 squared. 0.5 squared. So we can just get rid of this part. That's a good thing. So therefore, exponential of negative 1 over, okay, so here I can write 0.5 as 1 over 2, right? So I can write this one as 1 over 2. So 1 over 2 is 1 over 4. So if you put it outside, you get 4 here. So I can just get rid of this part. I put 4, and same for this part. Get rid of that, and that's just 0.4 here. Okay, so 0.4 over 2 would be negative 2. This is also negative 2. Okay, good. So exponential of negative 2 x minus 5.5 squared would be equal to exponential of negative divided by exponential of negative 2 x minus 6 squared is equal to 0.7 divided by 0.3. So let's take natural log from both sides. So one thing we should remember about logs is a log of a over b is simply log of a minus log of b. So that would be, therefore, log of exponential negative 2 x minus 0.5 squared minus log, that is natural log, by the way, e negative 2x minus 6 squared is equal to log over 0.7 divided by 0.3. And another thing we should know is natural log, so log of anything is just that power. So we can just write it as that. So negative 2 x minus 0.5. Oh, it's 5.5. I'm sorry, that's my mistake. This is 5.5. So that is minus 5.5 squared. Minus minus is plus 2x minus 6 squared is log of 0.7 divided by 0.3. So we have minus 2 times x2 minus 11x plus 5.5 squared, which I need to find out. So 5.5 squared is 30.25. 30.25 plus 2 times x2 minus 12x plus 36 is equal to log 0.7 divided by 0.3. And again, this is natural log, so in your calculator is ln. So we have negative 2x2, which will be cancelled by this 2x2, so we get rid of x2's. We have 22x here, we have negative 24x, so negative 2x. We have negative 60.5 here, we have positive 72 here, so 72 and 60, so plus 11.5 is equal to log of 0.7 divided by 0.3. So let's find this. Log of 0.7 divided by 0.3. This is this is 0.367. Oh, I took log, I guess. That was wrong. I should take ln. So that's ln. I am sorry for that. That is 0.847. 0.847. That is 0.847. Therefore, 2x is equal to 11.5 minus 0.847. Therefore, x is simply 11.5 minus 0.847 divided by 2, which is 11.5 minus 0.847 divided by 2 is 5.32. Is 5.32 or 33. So what we found is that the height that guarantees that you belong to female is less than 5.3. So that doesn't guarantee, that's more probable that you belong to females. And if you are taller than 5.32, then you're most likely to be male in this group. So as you saw, dealing with these functions are extremely hard. It's too cumbersome to work over the boundaries of x's, and that is why there are simplifications of these that help us. And the simplification of these are some function called discriminant analysis. The discriminant scores. So the discriminant score is a score that is given to each category for any x, and that is x times mean of that group divided by its variance minus mean of that group squared divided by 2 times the variance plus log of pi k. So this log is actually log in E, and this is ln. And this is called a linear function of x. So what is that? That means for any x, you find the discriminant score for each group. And based on that, you just simply compare the values of two groups. If the group that has a higher discriminant score is more likely to contain that group. For example, in our previous example that we explained, where we had, to remind you, I suggest you write these numbers somewhere, or maybe you just use the top part of this to find that. So as you can remember, we went a long way to find whether or not a person who is 5 feet belongs to males or females. So here we can use discriminant scores to simply do that. And to remind you, discriminant scores for each category was x times mu k divided by sigma 2. Was it divided by sigma 2 or sigma? Let me double check. Yeah, sigma 2 minus mu k squared divided by 2 sigma 2 plus log of pi k. So let's find the discriminant score for females given x equal to 5. That would be 5 times mu k, which was 5.5, divided by 0.5 squared, minus 5.5 squared divided by 2 times 0.5 squared, plus log of 0.3. For males, delta of males, for x equal to 5, that is 5 times 6 divided by 0.5 squared, minus 5 squared, 6 squared, okay, 6 squared divided by 2 times 0.5 squared plus log of 0.7. So let's calculate these two numbers. Okay, the first, so let's put x equal to 5. Okay. So this is x, this is mu, this is sigma, this is pi, this is female, and for males. So x was 5, mu was 5.5, and 6, sigma was 0.5, pi was 0.3, and 0.7. So discriminant score is basically equal to this x times mu divided by sigma squared minus mu squared divided by 2 times sigma squared plus ln of pi. Okay, so for females, the discriminant is 48. For males, it's 47.64. Therefore, so let me write it down. This one is 48.29. Yeah. So for females, it's 48.29. For males, that was equal to 47.64. 47.64. That means it's more likely that value would be female. So as you can see, the discriminant scores are shortcuts to just work on the probabilities of belongingness to each category. And one good news is, if you want to find a boundary, it's extremely easy. So if you want to see what is the discriminant boundary between males and females, the only thing you need to do is to equalize these two numbers. And you can generalize it to more than 2 categories as well. You just do it 2 by 2 and just decide based upon that. So females, you had x times mu k, which was 5.5, divided by 0.5 squared, plus, no, minus 5.5 squared Is it squared? Sorry that I have to check. I want to make sure we are on the right track. Oh. Yeah, squared divided by 2 sigma 2 divided by 2 sigma 2. I missed. It's funny, I just missed where I wrote things. It's very hard to work with this mouse when you're writing these things down. Okay, so let me use another one. This will be faster. Okay. Oh, this is annoying. Okay, so basically we want to equalize the two discriminant scores that we have. Oh, I just passed it. I don't know why it continues going up. Where it should stop. Okay, it was here. 5.5 squared times 2 times 0.5 squared plus log of 0.3. That should be equal to x times 6 divided by 0.5 squared minus 6 squared divided by 2 times 0.5 squared plus log of 0.7. So the x that solves that is basically x equal to 5.3 that we found before, and that is where the boundary exists. So the point I want to make is that when you use discriminant scores, it's extremely easy to find the boundaries. And as you can see, this is a linear function on x, and that's why it's called the linear discriminant score. And you can show that if you have two classes, basically the boundary is always the average of two averages of those classes. If you have two classes and the prior probability is 50-50, that's always the case. Try to prove it. Try to show that. Okay. So here we have some examples. So we simulate data based on few observations on a normal distribution with mean -1.5 and standard deviation 1. The variance and standard deviation is both 1. And so does for mu2. So here, based on this distribution, we can see there's a very limited number of observations. If we had more observation, it would look exactly normal. But even with that limited observation, we had two groups. This is the pink one and green one. And as you can see, in reality, the actual boundary is that dashed line, which was 0, because that's the mean of these means. But even with these few observations, you can see the boundary we get from simulated data is very close to 0. Though it's slightly biased to negative part, but it's extremely close to 0, and that's very powerful. So the main assumption in linear discriminant analysis in LDA, our main assumption is that sigma 2 is the same for all categories. So that's our main and major assumption. In order to find out sigma 2, you first need to find the sigma of each category. So sigma hat k is SD of each category. And then you take a weighted average of each category variance to get the total variance of which represents all cases. For example, let's say you have only 5 observations. So let's say 1, 2, 3, 4, 5. 2 are males, 3 are females. So pi hat of male in this case is 0.4. Pi hat of female is 0.6 because we have 3 females. And here, let's say you have found a sigma hat of, let's say, height for female. The variance of that for female, let's say, is 0.5, and the variance for males, let's say, just for the sake of example, is let's say 1. So here, what it says is that sigma hat 2 would be equal to NK is number of guys who are number of people who are male. So that is 2 minus 1 divided by total number of people were 5. So 5 minus K is number of categories. How many categories we have? We only have 2 categories, female and male. So 2 times. Sigma had 2 of males, so that is 0.4 plus. How many females do we have? 3. So 3 minus 1 divided by 5 minus 2 times 0.6. So we use this sigma to represent both categories. We can extend linear discriminant analysis in a higher dimension. In order to increase that, we have to use the multi-variable normal distributions. And in order to do that, what we need is a matrix of variance covariance. So let's say we have 2 variables, x1 and x2. Sigma, which is called the variance covariance matrix, has variance of each variable on its diagonal elements, and it has covariance of variables in diagonals. For example, here the covariance of x1 and x2 is -1, the variance of x1 is 1, and the variance of x2 is 2. So it's not too hard to say in this matrix form. We can just show that the density function of this normal distribution looks like this. And depending on how much covariance is between the x1 and x2, if there is any, we get different bell shapes in 3 dimensions. So here we have a 3-dimensional shape of a normal curve, which is based on 2 variables. If we just cut this function by this plane, what we get is just simple normal distribution that we know. So the x1 and x2 here are independent, and that is why we get this beautiful normal shape curve. Here there is covariance between x1 and x2. That is why it's just like it has a different shape. But the point I want to make is that even when we have more than one variable, the discriminant function can be written linearly on all variables. So the math behind it is none of our business now, but what the point that wanted to be made is that these linear discriminant functions can easily be categorized, easily. And that is true for all linear functions, so long that for different categories, this sigma, which is the variance covariance matrix, are the same. So here we have a simulation of 3 variables, 3 different categories, the orange, blue, and green. With each category has 1/3 chance to happen. So here are some simulated data on each one of them. We have green observations, blue, and orange. So the actual boundary is that dashed part, but you can see that by linear discriminant analysis we can easily get these linear boundaries. That's partially why we call it linear discriminant analysis, and it's very close to actual boundaries that we should got if we had more and more observations in reality. And here is Fisher's iris data. Fisher's was the first person, a great statistician who came up with LDA algorithms, and he used that to categorize different iris types. We have 3 iris types: blue, red, and green. They have 4 different characteristics: sepal length, sepal width, petal length, and petal width. And as you can see, these categories are very nicely separable. So he used LDA and showed that he can easily separate the 3 categories. And one thing great about discriminant analysis is that you can always project it to k minus 1 dimension. So if you have three categories, you can easily, irrespective of how many variables you have, you can always get two-dimensional functions to show them. So that's easy to see. And another wonderful thing about discriminant scores is that if you want to find the probability of each case belongs to another case, the only thing you need to do is just put it in exponential functions. For example, let's say, just for the sake of example, gamma hat of being female for x equal to, I don't know, 5.25. Let's say, just for the sake of example, is 2. Gamma hat of male for the same height is 1. Then you can show that the probability of y being equal to male, given that x is equal to 5.25, is simply exponential of linear discriminant function of male, which is 1, score of male, plus same thing, plus that of female. So the probability that person is female is exponential of 1 divided by exponential of 1 plus 2. So exponential of 1 divided by exponential of 1 plus exponential of 2. So it's 26%. 26%. So that is extremely powerful because you can just use discriminant function to find probabilities. And let's say, just again for the sake of example, let's assume we have 4 groups. Let's assume we have 4 groups. Let's assume we have 4 groups. And let's assume we have pets, children, adult females, and adult males. So let's say pets are normally distributed with mean 4, standard deviation 0.5. The height of pets, let's make it 3 feet and half, 0.5. Children 4 and 0.5. Females 5 and 0.5. And males, let's say 5.5 and 0.5. And let's say there is 10%, 40% chance that you have a pet in your population, 30% children, 20% females, and 10% males. And let's say you just randomly pick an object from this, which can be male, female, children, or pet. And you know that the height of that thing, which can be a human being or a pet, is 4.25. So you want to see what is the probability that is children, what is adult, what is pet. If you just want to do that through Bayes, it's extremely hard. It's extremely cumbersome. It's extremely long. So I'm not suggesting that, but you can easily find the discriminant scores for pets. So let's say for x equal to 4.25. Do the same thing. So let me call it gamma delta 1. You can do it for children. Let's call it delta 2. You can do it for females. That will be delta 3. And males, let's call it delta 4. Then the probability of that being pet, given x is equal to 4.25, is simply exponential of delta 1 divided by exponential of delta 1 plus exponential delta 2 plus exponential delta 3 plus exponential of delta 4. So that's extremely powerful. So usually when you have 2 classes, you assign it to one of the classes if there is more than 50% chance that it's happening. So let's say we are working with default, no default data. If the probability of default is more than 50%, you assign that to default case. If it's less than 50%, to no default case. So here is our using LDA on our credit card data, linear discriminant analysis on our credit card data. So here we had a bunch of variables. I think we have 10, 11 variables, and we just wanted to predict the default status. So here, 9,644 times we predicted no default, and it was actually no default. 252 times we predicted no default, it was actually default. 23 times we predicted default, and it was actually no default. And 81 times we predicted no default, and it was actually default. So our error was 252 plus 23, which is 275 out of 10,000 cases. So our error rate was 2.75%. Only 2.75% misclassification rate. So you may say, we may be overfitting, that is fine, but you may say that's an extremely good result. But if you're a manager, if you want a manager, to not be a good result at all. Specifically because if you just categorize every single one as default, then you predict 9,667 people correctly, right? So the error you will make is only 3.33%. So 2.75% in that sense may not be extremely good. But the major problem is, let's look at the real defaulters in this case. There were 330 people who actually defaulted. You only predicted 81 of them correctly. So you almost have 75.7% error in that case. And that is so dangerous for banks because they want to refrain from giving loans to these people. So we should have better predictability. How can we solve this problem? That's a question we have. And the way you can do it is to be more stringent on no default case. Now the threshold we had was only 0.5. So that means whenever some person has more than 50% chance to be a defaulter, you would categorize as default. What if we just change this threshold to 0.1? So even if you have 10% chance to be a defaulter, I categorize you in default. Of course, that's a better strategy for defaulters, but by being too harsh on people, you would just categorize more and more people in defaulters. So the extreme case will be that we set this to 0. If we set this to 0, then you will put everyone in default case. So you predict all defaulters correctly, but no defaulters will also be a victim of your very strict policy. So we can change this threshold to see whether to change the misclassification error. So at the beginning, in the previous case, we only had 0.2% default, no default people who will misclassify as default, and 75.7% as defaulters who were here. But by changing this threshold, we can change this probability. So here we have this blue curve. Okay, so let me first explain what we have. Here we have error rate. Here we have different thresholds. So 0.5 is our actual threshold that we just studied. In that part, 75% of our defaulters will misclassify. So the error rate for defaulter, which is this blue curve, is 75%. The error term for no default is extremely low. It's close to 0. As you can see, it's extremely low. And the this is the orange one. The orange one relates to those who will not default. So the error rate for misclassifying those people were extremely low. So the overall error rate was this much, which was 2.3%. So if we just push the threshold back, let's say at 30%, instead of 50%, we change our threshold to 30%. Our error rate for defaulters will decrease from 75% to 50%. And the error rate for no defaulters will change from 0.2% to around 1%. So as you can see here, let's say at 0.1, the error rate for defaulters changed to around 5%, but no defaulters to 21%. So depending on how stringent we want to see, you see a big jump in change in no defaulters by 10%, and after that everything becomes stable. But you see that the error rate for no defaulters increase substantially when you have more and more thresholds. So if you want to have less no defaulter error, it's better to stick somewhere around here, because after that the overall rate of misclassification decreases slightly, but you substantially decrease it from what it was before. And one thing I have to emphasize is that the overall error rate, which is the error rate for defaulters and no defaulter, is minimized right at 0.5. Nothing can beat it, and after that it starts going up. And here is our ROC curves. You can show that the power of the test and type 1 error simultaneously for different thresholds. You basically want to have a model that, oh, I'm sorry for that. A model that is closer and closer to this part. So if you have a model that is closer and closer to, oh, I don't know why I cannot draw a straight line here. So ideally, you want to go this way. And the area beneath this curve gives you an understanding of how well your model is doing. If it is right here, so if everything you have is just touches 1, so 1 times 1 divided by 2, the 1 times 1, which is 1, has 100% predictability. So here is our ROC model. So if you want to compare two models side by side, you can use ROC scores. The one that has corners closer to this corner are better. Okay, so let's stop the course right now. I am going to come back to quadratic discriminant analysis in my next video. Thank you for now.